Alright. Looks like we're live. Willkommen. Today, I'm actually kind of excited because we're actually going to start covering new stuff. For some reason, most of the things we've been looking at so far have been like semi-recorded. I guess that's did not expect that to be where half of the first, half dozen episodes would focus, but that's fine. Today's where I actually start to looking at sort of talking about new ideas and how new technology could work. In particular, there's one idea I'm very excited about. You'll see. But just as a background, if you've been around for a few years, especially in sort of the higher performance web community, you know that WASM is a thing, WebAssembly, and it's pretty neat, right? Theoretically, it should be able to give us this sort of machine-like runtime for not just web applications, but any web-enabled environment. And for that matter, turns out it's also just very flexible in general, but it still feels in terms of adoption, with a few edge cases here, like running DOSBox in the browser or whatever for old games, it still feels like it's stuck in a little bit of a niche. I don't see it being used as much as its potential could be used. So if you're not writing in an environment or context on a team that's specifically set up to support WASM, then it's going to be very difficult to adapt to. It's going to be very difficult to add as just like a one-off, right? And if you're not using a language like Rust on your projects that builds to WASM fairly easily, even if you're using like C or C++, there's going to be a lot of wrapper crud around that to, either hooking in Scripton or writing your own custom binding layers, and that's on both ends, right? Like as you're building the code and as you're consuming it too on the other side. You could use WASM modules in web applications, but if you've ever tried to do it, there's a significant lack of transparency compared to like developing Python in your IDE or doing JavaScript in the browser where you can drop in breakpoints, etc. There are some extensions for that, and there's some degree of support for that, but when it comes to feeding that back into the development cycle, it's like, oh, well, there was, this is the breakpoint in, that it shows me in debugging in the browser, in the stack instructions. But how does that feed back into where the assumption went wrong in your actual source code, right? How do you actually figure out what to fix? That's a different matter entirely. That just raises the barrier of adoption. That makes it more difficult to use for average developers, and it makes it less likely that WASM becomes widespread. And I'd say the third option here is really sort of the binary data interface. Here is this is a little, 2019, a little outdated by now, but here is the WebAssembly spec. This is it. Like, it's a surprisingly, it's really well written. It's a surprisingly succinct spec, and it's really interesting to actually just open up and read through. But you'll notice, among other things, like the support for types, for example, is extremely limited. Because remember, WebAssembly is like as an assembly analog. It's basically just stack machine instructions. So you're not talking about sophisticated data structures. You are talking about manual allocation. The degree of support for like smaller unsigned integers is very limited, and of course, there's no like built-in string, right? So you can look at more details. I'll probably paste the link to this document, maybe an updated version of it with the other materials, but it is worth checking out. But the real point here is that the binary data interface poses strict limitations, or at least obfuscations, on what kind of calls you can make into a WebAssembly module. Not to mention, and memory buffers too, for that matter. But that's a little bit more built into the actual interface of your runtime, regardless, because it has to be. And then, of course, like dependencies across modules. How is one WASM module going to call another module, right? Like you can't build everything in a one heaping module that only has one page of memory space. So there are clearly some drawbacks, and I think between those 3.5 reasons or so, we have a pretty good understanding of why WASM hasn't taken off the way it could have originally. So really, what can actually happen with it now? Does it have a future? I'm pretty sure the answer is yes, as it turns out. And I think one of the key missing ingredients is something you might have come across or heard me mention before, which is a relatively new programming language called Zig. Zig is pretty cool. Uh, probably the easiest and most common way to explain Zig is that Zig is to C as Rust is to C++. That's not entirely accurate, and there's a lot of ways you can nitpick and slice and dice that. But for our purposes, it's probably good enough. More to the point, Zig has fewer assumptions built into it when it comes to things like memory manipulation and allocation, deallocation. And it's more focused on replicating a cleaner, more modern version of the C paradigm in a way that's a lot more developer-friendly and easier to use. You spend less time fighting the compiler at the end of the day, and the compiler is there to help you, which is a nice feeling. It is not very mature, but it is built on the LLVM stack, so even though there's not a lot of tooling, or like the core module piece is still missing to a large degree. The standard library is excellent, but beyond the standard library, when you start looking for basic things like regex parsers or a CSV module, it's not there. So you're going to try and, especially with how quickly it's moving, you're going to try and grab someone else's tool, and it may not work, and it may break, and it may be compatible with a different version, etc. So there are some pros and cons, but especially with the LLVM compatibility, one of the big priorities for Zig is being able to build to any platform from any platform. And so that means that any platform can build to WASM, and therefore you can be doing your development, if you're targeting WASM, in Zig anywhere. Write it once, build it, it can be consumed, right? So, and then like the lowest hanging piece of fruit in terms of synergies, of course, is the memory allocation, right? Because you're going to need a custom allocator for WASM anyways. You might as well use a language that's built around well-structured allocation and deallocation and deferment. So a lot of these things make sense. And it's one of the reasons that Zig and WebAssembly are so well suited for each other. So there's a lot of really interesting projects, but this guy captured my feelings pretty well if you look at just how well synergized the two technologies are. So let's take a look at generating some WASM in Zig. What does it look like? We'll start off with a basic, traditionally like it's an adder function, right? But we'll, just to show some of the floating point behavior, we'll just square root instead. So let's write an exported function in Zig that just computes the square root. And let's say 32 integer returns a 32 integer. Already you know, right, that this is going to map exactly to the 32-bit floating point WASM type for the argument and for the return value, etc. Blah, blah, blah. So in this case, we'll use the stem mass square root. Voila, right? So obviously, this is an academic example. There's a lot more that you could do, and a lot of people have done some really interesting stuff on the internet with sort of demonstrating the cool browser-based applications you can build with Zig and WASM. Let me see if I can find one of the cooler examples here. Was it Zig Toys? I want to say it was Zig Toys. So here's. Might as well share this. Build. This guy's done a lot of interesting look into sort of how you can fix the data type and sort of application flow problems that you would otherwise run into. I'll paste this link as well. I thought he had screenshots of some of these applications. Now I'm going to make a fool of myself because I thought I'd check this out. You know what? Let's just... Maybe I can just pull it up on the page. Cross your fingers. I'm guessing I have to host this. Oh, wrong one. There we go. Yeah, pretty cool stuff, right? So this is all in Zig. Whee. So, we could take a deeper look at the source section. It might be interesting at some point, cover that article at some other point. But for now, let's look at this more academic example. So how are we actually going to use this? So one of the caveats of Zig is that I think the release schedule is like 2 minor versions a year, with 1.0 considered to be like when it eventually happens the final release in language. So it is moving pretty quickly, and something built for 0.10 is not going to work for 0.11. It's not going to work for 0.12, etc. So the nightly builds, on the other hand, are nightly. And so there's actually a pretty good intermediate release cycle that's comes about as the I thought I had this bookmark too. There's a game engine written in Zig that's used for some pretty interesting things called mock. And because it's a pretty serious line of development, there we go. It's pretty important to them they have stable versions to build against. And so they basically nominate releases. So I think if you keep track, instead of somewhere between nightly and minor release versions, you can use the nominated Zig versions from mock. And so, okay, this is a specific schedule and fairly stable targets where you can have some degree of assurance like this will actually build, right? So in this case, you can see we're going to go, let's say 1685 from the 0.12 release is what we'll target for now. Why is that relevant? Because a lot of the newer build tools in particular are still fairly unstable with how you handle dependencies. You can get them to work, and they can work consistently, but as far as reusing other code, I would struggle to recommend considering the mock nomination schedule. So when it comes to the building, in this case, we're going to focus on sort of a scripted build. Pretend this goes into a batch script or something like that, and just called build exe instead of having a build Zig script. Which isn't to say you can't do that too. You could automate a lot of that. But in this case, we just say we have a WASM target, and we have a specific export. We call it square root. I'm going to use 32-bit in this case. Theoretically, we go 64. There are some system alignment issues that I've seen that I'm still trying to figure out, but 32 will work in this case. So we have a build, and poof, we've created a WASM file. Like that's literally it. Before I forget, might as well add. Ignore here. Initialize. So we've generated this module. How do we actually consume it? And this, in my mind, is sort of the real brilliant part of WASM, which is because the spec is so simple, and because it's based on a fairly high-performance stack machine with well-defined interfaces, but still not defined in a platform-specific way, you could consume WASM from anything that has a WASM runtime. So we just wrote a fairly low-level, program. Pretend it's a more interesting application in what is nominally a systems-level programming language. But we could consume this from Julia. We could consume this from from a Rust program. We could consume this from Python. We can consume it from JavaScript, etc. So really, what we have here, if you think about it, is really like a modern platform-neutral version of a DLL, of a dynamic library. And so that's how we're going to think about this, and that's how we're going to look at the use case. So in this case, let's consider the possibility that we want to consume this in Python. So we wrote some high-performance code in Zig. It's being shared as a sort of, not necessarily obfuscated, right? Zig isn't very obfuscation-friendly anyways, but as a high-performance pseudo-binary, some sort of library that we want to use in other languages, and we'll try to use it in Python. So how do we do that in Python? There are a couple of options. My personal preference that I've seen more consistently platform neutral than most others is something called WASMtime. So I'll show you how to use that here. Import WASMtime, put it in our dependencies. What version am I using? Oh, that doesn't have a version field. Okay, we'll leave that for now. Okay, so first we set up a store. And that's basically address space, is my understanding. This next step is probably pretty familiar if you've ever instantiated WASM in JavaScript. We take the context defined by that store and we say here's our WASM file. And we now have a module that we can instantiate. So that's sort of the blueprint, right? We'll instantiate it, and then we extract our call point from the associated store, and now we can call it. I should say 2. And finally, sure we call the main closure integrate. And that's it. So you need a well-defined memory space and context, and you need to still instantiate the module. But this is one-time setup, right? And then you extract the entry points, call points, and you're good to go. The runtime handles most of the conversion for you, and we can go ahead and test that that's working. Let's see, what do we call it? Main pie. Oh no, it didn't work. What did I mess up? Oh, you done goofed it, Kirk. You done goofed. 32, square root. Store square root. You didn't like that. Wow. I even practiced this beforehand. Oh, is it the cast tag? Store context? No. Instance. Exports. Store. Engine. Module. Square root. Wow. Has no attribute context. I messed up the arguments, didn't I? Ah, right. We need to pass in the store as one of the arguments to the call. There we go. Forgot about that. The store is reused so often here. I do wonder, although I'm not focusing on WASM time today, like if there's a better way to streamline all this and set it up. But there we go. That's it. So now you can call high performance functions from Python. So this is really more like a sort of a platform neutral Python alternative, right? Or really any FFI or shared library replacement. But you can, it's not difficult to envision a way in which Python developers and Zig developers could work together in a very effective way, with the lower level, higher performance tools being exposed and very easily callable by Python or anything else with WASM runtime. So which is what I mean by using this as, or viewing this as sort of a platform neutral dynamic library of types. So that's how you would generate it, that's how you would consume it. And there's probably other examples we could look at that I won't spend too much time with today, but this is, again, a very academic example. Serious use cases for heavy lifting and like dozens of people working on high performance projects are going to take a lot more consideration. And as I've poked into this, there's a couple of 4 specific problem points that seem to be popping up across different use cases and projects. And most of them are related fundamentally to that issue that I mentioned earlier of the data types of the interface. So you have to be able to handle more complex data types. You need to be able to define them. You need to be able to instantiate them. You need to be able to pass them to functions. You need to be able to extract information from them as that information is returned from the methods you're calling. Obviously, you don't need to go full object-oriented, but you need to be able to pack data in structs. You need to be able to not just be dealing with, single 32-bit signed integers. Most of my use case and applications are like numeric work, so you're going to need to figure out some sort of way to pass like large sets of tensors back and forth, or at least define them in a shared memory space and be able to understand them on both sides, which is probably going to come with lock issues as well. So for a given struct, you'd need some sort of possibly factory function of some kind. There are ways that you can automatically transcribe that into a data class in Python using the FFI libraries if it's defined in a header, which could be compatible with Zig2. Define it in .h and reference it in the Zig code. I would rather do that all in Zig and return a factory function if you can, but of course the data class approach in general is going to be Python specific anyway, so trying not to back yourself into a language too much, a factory function seems like a better approach. You also need to be able to pack those structs in compliance with the C ABI, because the WASM linker in LLVM, if I'm not mistaken, is where you run into problems, still requires, or maybe it's on the Python side actually. No, I think I was right the first time. Still requires C ABI style packing for your struct fields. Of course, the next big issue here is going to be strings. There's no, if you look at the data types in here, there's no strings defined, except insofar as Zig treats strings, which is a set of unsigned 8-bit integers, which is a very useful way to think about it. And it's actually one of the things I like about Zig. But as far as sharing that information, how do you know how long that set is going to be? How are you structuring it? If there's string fields, lastly, to combine all those problems. If a struct has a field that is a string, how well defined is that packing? It's not. There are ways to build it, but there are better ways to build it than there are to consume it. So I don't know, maybe that's something on the WASM time side, but it's clearly some potential issue that you need to figure out. At the end of the day, though, why do we actually care about any of this? Keep in mind, Python was kind of an arbitrary example. We don't want DLL hell. We don't want, crazy obfuscated binaries, but we do want high-performance binary code that we can share to be able to run in any environment, and to be able to run very effectively to ensure we have optimal solutions. And to do that in a platform-neutral way would be fantastic. So WASM runtimes would be nice if we could push in that direction. You could generate with other things that aren't Zig. My preference here would be Zig, but there's still some, you have to figure out the numerical methods. You have to figure out, how are you passing the function signatures for integrators or optimizers? How are you going to handle tensor math? How are you going to do science and physics modeling? Of course, these are things more relevant to my day-to-day work, but there's a lot of lower-level software tools there that if you write those in Zig in a way and then provide them in a high-performance way where Python can consume them, that's a lot like TensorFlow did, right? Or PyTorch for lower-level tensor manipulations. And think of the world that unlocked and how much more we could do if we did more of that at the Zig level and sharing it at the WASM level instead. As WASM artifacts. You could even do engine-style stuff, like an ECS-style engine. You could easily imagine component specifications being defined in well-structured structs. Say we have sets of these components, and then your individual subsystems, systems or subsystems, are defined in their own WASM modules. You can throw them asynchronously as needed at a certain cycle or a certain cadence as part of the game loop. That, I think, would be a pretty powerful approach. You can also take that and reuse it too. So I'm coming primarily from the modeling and simulation background, which means we have a lot of redundant and rewritten code and algorithms between sort of the work that we do, and then when you hand it off to flight software, it's completely redone from scratch. They need to make assurances about, well, performance for starters. MATLAB, you can't fly garbage collected software. You need to be able to do, let's say, static analysis. You need to be able to make a security assurances. It needs to run with the right hypervisor. You can have different microprocessor architectures. All these things are things that lend themselves very well to writing these sort of behaviors, these sort of algorithms in Zig, because you can use them on the ModSim side. You can use them on the flight software side. You can allocate as needed with whatever the context is. And you can be able to target, whatever the processor architecture is for your flight system and still be able to run it in a high power computing cluster for your Monte Carlo studies, etc. So there probably one example I could share here is like, this is an interesting tensor, like Zig-based tensor library I came across the other day. And writing this in a way that we could adapt it to WASM interfaces would be just fantastic. This would unlock a whole bunch of interesting use cases. So as you can probably tell, this has got me a little bit excited. I'm pretty optimistic about things that could be done here. It's not even specific to Zig, though, but we went with Python because the Zig-Python combination, I think, especially culturally, is one that could work really well. It's just got some ways to work. So feel free to replicate this, mess around with it. I'll try and like share updates as figure out some of those data interface issues in particular. Really, like they're in addition to some of the other sort of core module analog things that I want to try and figure out on the Zig side and the Zig tooling environment. The line for success for me here would probably be something like being able to do the tensor-based physics modeling and optimization at the Zig level, where you can call it in Python, or of course, call it from anything else. Do it from a web browser or whatever. That, in my mind, would be, or state machine modeling would be pretty neat too. That would be pretty darn cool. So we'll see if we can get there. Maybe we'll throw a few more projects or sessions at it, but that's sort of where my head's at, and one of the more interesting or brighter sides of the applications of Zig that I'm seeing. It's also how I think WASM could make a comeback, because while it's not dying, I think a lot of the WASM hype has passed, and I think at this point we can start thinking about what the long-term WASM future looks like. Who knows? Could be this. Cheers.